quantum mechanics, at least to start with. And that's going to consume our attention for most of this class. In other words, we've got plenty to do in the non-relativistic thing. So our focus initially is non-relativistic quantum mechanics. We'll bring in some relativity down the line, but we'll kind of do it as an add-on, not the main thing. By the way, the person associated with relativistic quantum mechanics is this Nobel Prize-winning physicist by the name of Paul Dirac. And Dirac is an interesting character, hardcore non-believer, by the way, hardcore, and it's speculated that he was autistic. The best that can be said of him is he had very low interpersonal skills. He just really, people go on and on, talking to him, he'd answer yes or no. Yes. After you go, da 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 da, yes. No. So interesting character, but absolutely off-scale brilliant. Quantum mechanics doesn't have a single originator like Einstein really was the big cheese in relativity. There are a whole bunch of people that contributed to the development of quantum mechanics. And let's just name a few of them. So we have Dirac, did a lot, and you probably know some names too. And Einstein, as we mentioned, did a lot. The famous Niels Bohr did a lot. Heisenberg, for whom the uncertainty principle is named, and we'll revisit that uncertainty principle in some detail. So Dirac, Einstein, Bohr are biggies, and then there's Pauli exclusion principle, and the list goes on. These are some of the biggest of the big boys. Oh, Schrödinger. And now we have Professor Schrödinger up here. Do you want to hear kind of a risque story about Schrödinger or not?
Yeah.
Oh, I knew you would. Well, Phoebe, I'm sorry. You were outvoted 2-1. Schrödinger and his wife apparently were not getting along the best. They weren't on the best of terms. And so Schrödinger had arranged a retreat to the mountains somewhere in the Alps, ostensibly to work on science. But he was meeting someone there as well. Schrödinger had 3 simultaneous jobs to do. Okay, he had to successfully deceive his wife, entertain his mistress, and invent quantum mechanics over the Christmas break. 1, 2, 3. Now, I don't know how well he entertained his mistress, and I don't know if his old lady caught on, but in this steaminess of passion and enthusiasm, he developed the wave formulation of quantum mechanics.
Nice.
Isn't that a great story? I'm inspired.
Is that pretty true as well?
Apparently, I'm getting it for second or third hand sources. So if you're curious, you can see what the internet has to tell you about his exploits. By the way, Feynman, we'll put his name down. Feynman was quite a womanizer, and also a Nobel Prize winner. get into what quantum mechanics is and how it works and see what we're going. So basically, classical mechanics and classical electricity and magnetism don't fit the data. They don't fit a bunch of experiments. And they don't fit, as we said, when you get out of that low velocity and large mass region. Tiny things moving fast, Newton goes away. Michael Faraday on the electricity and magnetism side goes away. James Clerk Maxwell goes away. Okay. By the way, we should add classical electricity and magnetism. And the architects of classical E&M are Faraday on the experimental side and Maxwell on the theory side. And just as classical mechanics, Newtonian mechanics failed, if you have high velocity charged particles, you've got problems.
I saw something somewhere, I forgot where it was on, but it was like it was Faraday, and like no one believed a lot of the things he was saying, and then Maxwell solved like a lot of the theories he was experimenting through like equations.
So that's exactly right. It turns out that, by the way, both Faraday and Maxwell were extremely devout Christians. And so they're interesting in that way. Faraday arguably is the greatest experimental scientist who ever lived.
Yeah.
Newton is the greatest scientist who ever lived. Okay, if Einstein says it, it's got to be true, right?
Didn't he like pretty much invent the motor, pretty much, like the first.
But yeah, so anything that you think of, motors, generators, all sorts of chemistry effects and physics effects, Faraday was an experimental genius of the highest order. I mean, incredible, unbelievable. But he could barely do basic algebra. I mean, he struggled with numbers and mathematics, but he was an experimental genius. Maxwell was a theoretical genius using differential equations, advanced calculus. The guy was just off-scale bright. People say that after Newton, I mean, it's been said that after Newton and Einstein, Maxwell, I mean, that's how good Maxwell was. By the way, he only lived to age 48.
Bummer.
Died of cancer at age 48. Young guy, you know. But together, so Maxwell, just what you said is right. Maxwell set Faraday's experimental insights into equations, and those are the summarized in the 4 famous Maxwell equations of classical electricity and magnetism. Not the thermodynamic Maxwell equations,
No.
he did thermodynamics too, but the E&M equations. So, but if you get high velocity charged particles, you got this classical E&M doesn't handle things like atoms and molecules. So you have classical mechanics failing, you have classical electricity and magnetism failing, and you have experiment telling you, hey, all your classical theories are not working. So this is a a beauty school dropout too, to use Grease terminology. Okay. Now. Okay, the basic results or explanation of quantum mechanics. The idea is energy is quantized into well-defined regions. You can have energy in any energy you want. You can have certain energies and you cannot have others. And you're used to quantization of money. You have, can you saw a penny in half and get a half penny? You know, in principle you can cut it in half. In practice, you can't, okay? And you can't take a dollar bill and cut it in 4 pieces and make four quarters out of paper. There's some restrictions. So energy is quantized into well-defined regions, and there are a whole bunch of consequences of that. Now, we'll learn how to quantize it, we'll learn why it's quantized, but there are some profound consequences with incredible implications for physics, for chemistry, and for biology. Energy is quantized in various regions, and possibly other quantizations would be like involve angular, particularly angular momentum, is a really big one. We might see angular momentum quantized. By the way, you're already used to this because you've learned about atomic angular momentum quantum numbers. The L quantum number from general physics is an example of quantized angular momentum. Okay, L equals 0, 1, 2, or the SPDF, which are, by the way, spectroscopic terms. Sharp principle diffuse and fine. Okay, so we're going to see that these consequences are significant, they're profound, and they will govern a lot of our understanding of chemistry, biology, physics, and devices and experiments that we use all the time. Okay? Now, the failures of quantum mechanics are incredible. And I want you to kind of put your mind back 100 or so years and think about what the physicists were facing. My goodness, theories that were incredibly powerful, that worked in all sorts of circumstances, were failing. It's like a college student who got straight A's for 3.5 years, and then in his final semester, don't you dare do it, you get a string of F's. I mean, what does a college do if someone's getting top grades for 3.5 years and then starts flunking all his classes? Well, you go in and say, is your mother dying? Did you break up with your girlfriend? You know, I mean, you know something has happened, okay? And we know why quantum mechanics didn't appear on the scene, you know, among other things, in the 19th century, the 1800s, experimental skill went to a whole new level of sophistication. Think of all the stuff that happened in the 1800s. You had steam engines, steamboats, you had all this precision lathes and milling machines that could mill parts to sub-10,000ths of an inch accuracy. I mean, that you just couldn't do stuff like that until the 1800s, and all this fancy technology, optics, everything. So the discrepancies came as a result of the precision that was available to scientists for the first time in the 1800s. And then you have all these flunks of classical mechanics and classical electricity and magnetism. Now, you want to hear some of the F's that classical E&M and classical, so here's a list of F's, okay? Atomic and molecular spectra. How do you describe the spectra of atoms and molecules? Red F for classical. No way does classical E&M do it. Black body radiation, red F. That was Planck's thing. Heat capacities of metals, red F. Molecular vibrations, red F. Photoelectric effect due to Einstein, red F. I mean, it'd be like if you flunked all your classes, we wouldn't want to throw you out of the university. What's the matter with you? You know, how can we help you? You know, and so they didn't want to throw their old theories out because they worked in so many instances. Yet they said that there are all these places where they're flunking. So there's the situation. Now, what we want to do is look at things in a quantum way. And let's see. We go in this class from
15. I think.
we go to a quarter after, right?
Yeah.
Okay.
Yes, we got time.
Okay.
Almost
Good.
30 minutes. Let me check this camera out. Make sure
Yeah,
it's-
let's do a camera check. Let's just make sure everything's rolling.
Everything's rolling. We have roughly around 18 minutes of film time.
Okay.
Wow.
No, of him going. We have like 100 minutes left.
Oh, okay.
So yeah, this SD card's good.
So yeah, so do we have like 25 minutes of filming?
Yeah, it'll be good.
Yeah, we're good.
Okay.
Need like an hour and it's a lot of minutes left. We're real good. Hour 40, hour 50.
Okay. Let's do a little work on foundations of quantum mechanics. We'll start with the total energy. There it is, E. And in general, the total energy is comprised of a kinetic energy piece, symbolized by capital T, plus a potential energy piece, that symbolized